I told you on Thursday, a couple weeks ago now, that the next thing we were going to talk about was improper integrals. I've decided to use my prerogative as instructor to change the order of things because I was thinking quite a bit on my cruise about the way in which this stuff should be taught. And at this point, I don't feel we have properly motivated improper integrals, right? Why it is that we would want to consider them. So instead, I want to jump right into sequences and series and use those as a way of motivating improper integrals. Now, I'll tell you the way, if you look in the textbooks, they are going to have improper integrals in there somewhere, and then they're going to get into sequences and series and use them. Right? But to me, this is actually the first real good application of them, other than some assorted volume problems that I would rather push off till a little bit later. So that's what we're going to do is we're going to start with sequences and series. Now, another difference between my presentation and what you'll normally see is that you will normally see sequences and series taught as separate things, two different chapters in a book, right next to each other. So this isn't a gross departure from that. But I really want to teach them at the same time. So with that in mind, I'm going to have to use two pieces of chalk, one for each hand, so that I can. Just kidding. Joke. No, but I would like to teach them at the same time, in sequence or in series, one of the two. All right. Now, sequences, we've talked about in the honors calculus section on Friday. So at least 60% of you have already seen these before. The remaining 40% of you, which would be 2, I think you'll catch up very quickly. I'm not going to talk about these things as precisely as we do on our Friday meetings, where we actually use epsilons to talk about these things. We're just going to be a little more hand-wavy about things, but it should be good enough. So the first thing is, what is a sequence? Right. So the way we're going to define a sequence is just a list. Right? It's just an ordered list of objects. Okay, think of your grocery list. Wow, actually, does anybody here go shopping? Actually, do you? Okay, so you guys have stores to go to. Okay, I don't know how it works, over here in Boston. Okay, so you go to the store, all right, and you make a list ahead of time. Okay, and there's first thing on the list, second thing on the list, third thing on the list, and so forth. Dina doesn't make a list; she keeps it all in her mind. But that's okay. You don't have to write it out; it's in your head somewhere. Okay, and if somebody says, "What's the 10th item on your list?" Assuming you've written out your list in a sufficiently ordered way, right? You can say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's the 10th item on my list, all right? And we're going to call that the 10th item in the sequence. Okay, just sequence list. We're going to use these synonymously. All right? Now, when you make out a grocery list, does there have to be any rhyme or reason to how you put them on the list? Eggs, cereal, pantyhose. Not me personally. All right. I can get the milk. I can get my cheese. I can put them down in any order, right? There doesn't have to be any connection between one item on the list and the next. Okay? And we want to have the same lack of restriction on our sequences. Okay? So a sequence is just going to be any list. Of course, we're not going to talk about the most arbitrary sequences in here. We're just going to talk about sequences of real numbers. Okay? So it's going to be an arbitrary list of real numbers. Okay? So sequence is a list, right? And by list we always mean ordered here. Okay, there's some ordering to it. It's a list of real numbers. So this is what it means for us. Okay, a list of real numbers. Now, let me just say, we're not going to allow things like gaps in the list. Right? You might be thinking, oh yeah, let's see, I'm going to put down like all my vegetables here, and then I'm going to put all my fruits here and all my meats here, or something in your list. And then you might leave some room in between the categories, right? Because I want to add in a few other things. Maybe I know I forgot a fruit down here, and I can't remember which fruit I needed for that recipe, so I'm going to leave 2 spaces or something. Okay? We're not going to allow that. You can't have empty spaces in our list. Okay? You have to have, everything in the list has to be filled up. Now, when you have a grocery list, there is a very special number associated to your list. Can you think what special number you have associated to your list? Yeah, the amount of stuff, right? How many things are on the list, right? That's a very special number associated to your list. If somebody says, how long is your list? You can say, I have 37 things on it, right? Okay, that's a very special number. Okay? So in mathematics, however, we can have lists that are a little bigger, right? How many things do you think we can allow to be on our lists? Infinite, yeah, all right. We don't have a shopping cart. Right, we got to keep it in here, right? Well, I only have so much money. I can't only buy so many things, or the store only has finite number of objects for me to purchase, right? Okay, we don't have to worry about that in math. Okay, so we actually have, in a sense, 2 different kinds of sequences. Okay? So a sequence is finite, right, if it has a finite number of what? What should we say? Entries? Terms? Yeah, terms? Terms of a sequence is a good word. Okay, what are the terms? The terms, all right, those are the numbers of your sequence. So we have a finite sequence. And what do you think it means to be infinite? What's an infinite sequence?
Endless.
What's that?
It's
It's endless. What do we mean by endless? Never ending, okay. Okay. Well, here, I'm going to give you a real cop-out definition. Okay, this is going to be, you're going to like this. Yeah? A sequence is infinite if it's not finite. Very good. If it is not finite. Okay. If you cannot associate a natural number to it and say that's how many terms are in the sequence. Okay, so we're going to look at finite sequences and infinite sequences. And, well, since this is calculus, which do you think we're going to be more interested in? Yeah, got to be infinite, right? We're looking at infinite things, right? Infinitesimals, things that get infinitesimally close, right? Adding up an infinite number of infinitesimally small things. Looking at the tangent line, which means you'd look at, as the secant lines get infinitely close to this point. Okay, right? We're looking at infinites with calculus. Okay, so that's what we care about. All right, so give me an example of an infinite sequence. Anything you like. Numbers would explain. 1, 2, 3, 4, so forth, right? Okay, so this is the natural numbers, right? And it forms a sequence. The first term in the sequence is 1. The second term is 2, 3, 4. I might be saying, wait a second, you said it's a list. Doesn't it have to go down? Right? Isn't that how you write your grocery list? Of course, it doesn't matter, right? You could write your grocery list like this. We're generally going to write our sequences, right, separated by commas. And this will be the first term, the second term, the third term, the fourth term. Okay. Do you agree that's a sequence? Okay, good. Do you mean another sequence? What's a famous one? Say if you watched, I don't know, the Da Vinci Code or something. You saw the movie. You must know the sequence. I'll give you a hint. Don't lie. That's not a bad hint. What's another word for lie? To lie is to fib, right? Fibonacci. Okay, so how does the Fibonacci sequence work? Right. 1, 1, 2, 3. Okay, so let's let's tell the story, all right? Do you know where the Fibonacci sequence comes from?
No idea.
No idea? Okay, so let's just say it. So Fibonacci, whose name was actually something like Leonardo of Pisa, he was interested in the following problem, and don't think he was a pervert because of this. It's a real problem. He says, okay, take a couple of rabbits, male rabbit and a female rabbit, okay, and you say they're born at the same time, and they're going to start having their little kids. Okay, so now what's going to happen? Well, he makes a couple of assumptions. Let's say that it takes 2 months for rabbits to start reproducing once they're born. Right? So after the first two, I know this is kind of, yeah, don't worry. Okay, after 2 months they start reproducing, and then they reproduce every month, and they have a new one. Right? That's the way it's going to work. So what happens? Well, and actually, I think the way he originally stated, you don't have a man and a woman. You just have one rabbit, and you can assume that it's reproducing asexually or something. So we use F for Fibonacci, right? And we'll say 1. Okay. In the beginning, you have one rabbit. Okay, it's born, and you have the one rabbit. Okay. Okay, at the end, so that's at the end. And at the end of 1 month, you still have one rabbit. At the end of 2 months, you still have one, or at the beginning of the second month, I guess, you still have one rabbit, right? Because it can't reproduce until 2 months. Okay, now after 2 months, it's going to reproduce and have one rabbit. It always has, every rabbit who reproduces only has one rabbit. Right? Okay, it goes up to 2. Right? So now there's 2 rabbits. Okay. Now, one of them is going to reproduce again the next month. Right? But the other one is not, because it's only 1 month old. Okay, so now there's 3. Okay, so here's your first rabbit. After 2 months, it reproduces. Right? After another month, this first one reproduces again. Okay? And this one doesn't, because it's not old enough yet. Okay? What happens in the next month? So let's see. So now you had these 3. Now this second one is now old enough to reproduce, and the first one gets to reproduce again. So this one reproduces, and this one doesn't. So you get 2 more. Okay, so you get to 5. Okay, so it starts looking like this: 1, 1, 2, 3, 5. And if you check the next one, right, it starts getting harder on your hands. Right, 3 of them are now able to reproduce, and so you're going to get 8. Okay. And so in general, it actually turns out that the number of rabbits, all right, after this first couple months, the number of rabbits who are going to be able to reproduce is exactly equal to the number of rabbits you had the previous iteration. Right? So at this point, the number who are going to be able to reproduce is only 5. And each one of them will, until you'll get 8 plus 5 new ones, so you'll have 13. So that's the next one. And, well, I just said, the way you're going to get the next term is you take the amount you have now plus the number who are going to reproduce, which is the amount you had the month before. Okay? So in general, right, this just keeps going. Okay? If I want to know how many I'm going to have in the nth month, I just need to add up how many I had the 2 prior months. Okay? Right? This is once n gets big enough, right? Namely, once n gets to 3. Right? So 13 is 8 plus 5, 8 is 5 plus 3, 5 is 3 plus 2, 3 is 2 plus 1, 2 is 1 plus 1. Okay? So this actually gives us a rule for the nth term in the sequence. Is this required to have a sequence, that we have a rule? No. Right? We don't need to have a rule. Okay? There just needs to be some entry there. But in this case, it's really nice we do. And things are going to be better if we do have a rule. Okay, okay, so this here is the, this is, oh, are there 2 B's? No. think that's the correct spelling. Up to a constant. It'd be better if I didn't know the number of C's, because then it's correct up to a plus C. Okay, so this is another sequence, right? So the sequence, right, you could write as 1, 1, 2, 3, 5, 8, 13, 21, and so forth. That's our sequence. And the way that we might write this down in shorthand, since we've used these F's, right, for Fibonacci's, we might write something like this. Right, we'll use little brackets and then we'll put around the F's. And then we might write n equals 1 to infinity, right? Infinity here just meaning it doesn't end. Okay, of course, in reality, you couldn't let these rabbits procreate forever. You'd have quite a problem. Okay, so this is the sort of symbol we want to use, right? So if we just want to talk about a sequence, right, we'll just write down the braces, and if we have a name for the elements in that sequence, we'll just write it down like this. And if it's necessary, we'll add the n equals 1 to infinity. But usually this bit won't be necessary. Okay. Does this make sense? I'm not sure it does. Are you happy? Yeah? Okay. Chris, happy? Yeah. Okay. Very good. So, okay, we got this nice sequence. This sequence turns out to be interesting in more ways than I can explain in the limited amount of time we have. An interesting question that you might try to do a little bit of research into is, it's not hard to find an answer, is there a way of computing the nth term in this sequence without having to do it recursively? See, if I want to know the 100th term in the sequence, what do I have to do? Well, F100 is F99 plus F98. So if I want to know F100, right, the 100th term, I need to know the 99th and the 98th term. Okay, well, how do I get the 99th term and the 98th term? You need to know the 98th term and the 97th to get the 99th. And you need to know the 97th and the 96th to get the 98th. Okay, this, you can see, could take a while, right? Right? You could start adding, you have to write all these things down, right? And this isn't, as nice as you think it should be, right? You should be able to just say, okay, the nth term is blah. Right? And, well, sometimes you can't do that, but in this case you can. And there is a really interesting formula where the golden ratio, which maybe you've heard of, pops up naturally. So this is very nice. Okay. So we're going to use this notation quite a bit for our sequences so that we don't actually have to specify what the terms are. Right? Because, of course, we always want to just talk about any sequence. We don't want to have to tell you what the sequence is. Right? So we'll use this notation a lot when we just want to talk about an arbitrary sequence. So I want to immediately jump in now to what the series is. And so let me just show you a really nice thing. Right? Let's let an, okay, so this is just my notation, right, for a sequence. And I'm not telling you n equals 1 to infinity here because I don't, or to anything. I want to leave that unspecified, right, just any sequence. So we let this be a sequence. All right, now the following notation is not standard. I've created it just for you guys. For every sequence we can of real numbers, we can immediately write down another interesting sequence. Okay, so we're going to take this sequence and we're going to write down another sequence. I'm going to call it the sum sequence. Okay? So we get the sum sequence. So this is another sequence. And the terms, well, I'm almost going to write it the exact same way. Only I'm going to put a plus on each of these. Plus, add, sum. Right? That's what we call the sum sequence. I'm going to pull a plus up there. Okay, now, This is absolutely useless to you because I didn't tell you what the sequence is. Okay, so what is it? Well, let me tell you them term by term. What's A1 plus going to be? A1 plus is going to be A1. It's the exact same number. About A2 plus. A2 plus is going to be A1 plus A2. I'm going to add up all the terms in the sequence up to A2. Not so many. Okay? Take a guess what A3 plus is. A1 plus A2 plus A3. Okay. And what about AN plus? I just add up everything up to AN. Another way to write this, right, is the sum I equals 1 to N of AI. Another way to write this, by the way, is AN minus 1 plus. What do I have to do to make this correct? What's the difference between these two? Missing AN, right? This adds up everything up to N minus 1, right? AN minus 1, right? So to get this, I need to add AN. So not a lot of different ways of writing these things down. Okay. This, again, not only is this notation non-standard, this word or sequence of words is also non-standard. I just think it makes sense for this. Okay? So you start with a sequence. You can write down a sum sequence. Let's do an example. Okay. Let's start with our sequence AN, where AN equals N. Okay, and N here goes from 1 to infinity. Okay. What sequence is this? It's what? It's a natural numbers, right? It's actually the first sequence that we wrote up here. Right? A1 is 1, A2 is 2, A3 is 3, A4 is 4. Right? So what is the sum sequence equal to? Okay, what are the terms? Let's see, what's the first term in the sum sequence? It's A1. Uh-huh. What's A1? 1. Okay. Okay. What's A2 plus? 1 plus 2, which is 3. Right? What's A3 plus? 6. Okay. We're getting somewhere. What's the next term? 10. Okay. One more. 15. Making you work on your addition. Okay. Okay, so we start with the sequence 1, 2, 3, 4, 5, 6, and so on. Right? And from that, we build a new sequence, the sum sequence, 1, 3, 6, 10, 15, 21, and so on. Okay. Now, let me specialize to a nice case in which we're not very much interested in. So let me go from n equals 1 to k. So let this be a finite sequence. a k plus is what? A1 plus, what does the plus mean? It means you're going to add, right? Sum, add. You're going to add all the terms up to AK, right? So A1 plus A2 plus A3 plus all the way up to AK, and this sequence stops at K. Okay? So this is the sum of the entire sequence. So this is a very special term, right? This is the last term in our sum sequence. Okay, now, there's something tricky about what I'm going to say next. These are all real numbers. If I add them up, what do I get? A real number. Right? Okay, so this is just a real number. I want to formally, I'm going to put quotes around this. Okay? And if I put quotes around one thing, I should put quotes around the other thing. Okay? I'm going to put quotes. And I want to consider this sum as written, okay, as an object in itself, not the actual answer, not the real number answer. I just want the actual expression. A1 plus A2 plus A3 up to AK. Okay? So, is it clear what I want? I don't want the number. I actually want the sentence that we're, right, the expression that we've written down here. Okay? So if I replaced this with just the number and kept quotes around it, that I don't want to think of that as the same thing. Okay? I want to think about this as it is. Clear what I want? Okay. I want to call this a series. Okay, when I have quotes around it, right? When I actually want this like this, right? When it's the sum of all of the terms in a sequence, I'm going to call it a series. Okay. And so far we're only doing this for finite sequences. Okay, so for a finite sequence, a series is the, and I'm going to write the word formal here, but I'll put it in parentheses because I don't really want you guys to worry too much about it. Right? Is the formal sum, okay, and in the finite sequence, this isn't an issue really, is the formal sum of all terms in the sequence. Okay, now, the question that should go through your mind at this point is, what's the fuss about? What's the difference, really, between writing down this finite sequence, adding them up, and leaving it like that, or just adding them up and getting a number? What's the difference? And the answer is, for finite sequences, there is no fuss. There's no problems. There's no worries. But where are the worries going to come from? From infinite, right? That's where we're going to have problems. Okay? We're going to define things in a very abstract way for the finite sequences, right? So that we can do the same definition for the infinite sequences and not have to all of a sudden change things up. Right? Because what's the problem? If I start adding up terms from an infinite sequence, what does that mean? Adding up everything in an infinite sequence. This is right. This is a little bit of a problem in our heads, right? And when do you stop? Well, you don't stop. It's infinite. You keep going, right? So, how do you just write down a number, right? So you can formally just say, well, I'm going to add up everything, and then just leave it like that. And that's what formal means. Okay, you just say, well, I'll do it, but I'll get around to that later. Okay, so that's where we're headed with this, right? So, but for finite sequences, there's no problems, right? You start with a sequence, right? You can build the sum sequence, and you can even write down the series. Okay. So series is just the sum of all the terms in the sequence. That's all it means. Okay? So you start with a sequence. The extra s is for sum. Okay? So you're going to add, that's just this one s that comes from sequence, right? The second s, that means you sum it up. Okay. Okay. So finite sequences. And mind you, I would call this a finite series as well, right? Because there's a finite sequence, you get a finite series. They're not very interesting to us, right? So what we're interested in is the infinite. Okay. So to talk about infinite sequences in an interesting way, we're going to have to talk about convergence of sequences. Okay? And let me show you why. So let's start with our first example of a sequence. Okay, so again, okay, so this is just, we have this sequence and an is n. Okay, that's the shorthand for the sequence of natural numbers. Yep. What is... Well, now I have a problem. If I want to write down the series for this, right? The series is, okay, you sum up all the terms. Okay, well, for an infinite, I have a notational problem because I don't have a number to put here anymore, right? For a finite, just put the last number right here. What should I put for an infinite sequence? Okay, let's suggest infinity. Okay, that's as good a guess as any, right? With what you should put. So, what is A infinity plus? Well, formally, we can write down, and we'll put some quotes here, A1 plus A2 plus A3 plus A4 plus AN plus, it just keeps going, right? And then you have to put some quotes at the end. Okay, so formally, it's an expression that goes on infinitely long. Right. And, well, we know what A1 and A2 and A3 are in this case. Okay. It's 1 plus 2 plus 3 plus 4 plus n plus, it just keeps going. Okay, so you start adding up these numbers, right? Okay, we're going to, instead of looking at the whole series, let's just look at the partial sums. Okay? What is a partial sum? Well, partial sums is where you actually just look, right, at these terms. Okay? Remember this 1 here, this was A1 plus. This 3 was A2 plus. The 6 is A3 plus. Right? The 10 was A4 plus. This was A5 plus. This was A6 plus. Right? These A1 plus, A2 plus, so forth, right? These are called the partial sums. Right? So the AI plus are called partial sums. Why partial sums? Well, sums is clear, right? You're adding things up. Why partial? Because it's only part of the sequence, right? You're not doing the whole thing. If you did the whole thing, it would be called the series. Okay. These are only the partial sums. Okay, so we looked at these partial sums. Now what happens to these partial sums? They get bigger, very big, right? And the farther out, they're just going to get bigger and bigger and bigger and bigger. Okay? So what's the sum of this going to be? Is it going to be a natural number? Right? If you add up every single natural number, do you get a natural number? Mind you, we're adding up all the natural numbers. And we're not stopping anywhere. Does this make any sense at all to do? Yeah, you never stop. Now, here's an interesting thing. Chris just said you never stop adding, so you never get an answer, right? 'Cause in your head, it's like an ongoing process, right? Every time you get to the next one, you still got another one you got to add, right? But let's just say I add them all together at once. No process, right? There's no procedure here. You don't walk along the route, oh, now I'm adding 12, now I'm adding 13, and then now I'm adding a billion, now I'm adding a billion and one. No, we don't do that. We just add them all together at once, one time. Is there a number that you get? No, you add them all together at once. Does that make any sense? Why not? No, there are no other ones. You took all of them, right? You took all the natural numbers and you put them into a bag. All right? They're all in there. And you say, I'm going to add up all at once, add up everything in that bag. Boom. Does it make any sense? Why not? Because it just doesn't. Well, let me ask you. If it did add up all at once to a finite number, right, to a natural number, would that cause a problem? Would that be bigger than all the natural numbers that you have? Oh, okay. So maybe Dina's worried about the following thing, right? Let's say you add up all these numbers, right? And you get k, right? You get some natural number k. Assume you add up every single natural number all at once, and you get k. Isn't k on that list somewhere? And then when you add 1 to k, you should get something bigger than k, right? So now you have k plus 1, plus a lot of other stuff, equals k. Well, that's just silly, right? You start with something and add to it. You can't, add something which is not 0. You can't go back what you started with. Right? Okay, so it then should be clear. You cannot add up all the natural numbers and get a natural number. Okay? If you stop at any point, right, look at any of the partial sums, you get a natural number. That's for sure. But if you do it all at once, you look at the series, okay, the series where you add them all up at once, it can't be a natural number, right? Okay, now, what was the problem with the discussion we just had? What's the problem? I'll tell you. The problem with it is my hands are doing this a lot. Okay? As soon as your hands have to start doing this, and you have to start saying things like, what was it you said? You said, because it can't, right? I mean, when you have to start using phrases like that, now you're in deep doo-doo, right? This is not good for mathematics when you have to start talking like that. And it's okay, it's not a diss or anything, right? This is a problem, okay? And it tells you need to define things, right? You need to be very clear about what you mean. Right? Okay, so we need to be a little more clear. Okay. And from those definitions, we're going to be able to decide when such a series makes sense to talk about, right, in a meaningful way, right? Talking within the set of real numbers, for instance, and when it can't. And those two notions that we're going to come from this are going to be called convergence and divergence. So divergence is going to be easier to define than convergence. So we'll start with convergence. So now we're just going to talk about infinite sequences. While I'm pausing for a moment. Okay. So let's let an infinite sequence. Okay, and I'm going to drop the word infinite most of the time now from here on, because we're always just going to be talking about infinite sequences. So we start with an infinite sequence. What do we mean that a sequence is going to converge? What do we mean that this is actually going to make sense? Goes to a number. What do we mean by goes to a number? Has a limit. Okay, so now we need to find limit. Right? What do we mean it has a limit? Well, we've talked about limits, of course, of functions. Right? We have limits of functions. What does it mean for a function to have a limit at a point? Okay, so what did that mean if I said the limit as x approaches a of f of x equals L? All right, let me write that. Okay, you have some function, and I said the limit as x approaches a of my function is L. What did that mean? What approached what? The function? What do you mean approached it from the left and the right? Of L? X? A? What are we talking about? Too many pronouns here. We don't want to use the Magnificent Seven if we can. Magnificent Seven is his, her, this, that, here, there, or it. Try to use those as infrequently as possible. Uh-huh. Okay, so I won't hurt you guys here. Okay, you guys are talking about these two one-sided limits, right? Okay, so tell me, what does this mean? Yeah? What does it mean that as x approaches a from the, which side is this? From the right, yeah, from the plus side here. What does it mean that as x approaches a from the right side, that f of x, right, that the limit of f of x as x approaches a from the right is L? What does that mean? What do you mean approaches? You mean? Okay, so that's an approximation here. Okay, so Dina's saying, tell me if I'm wrong, that as x gets close to a from the right, f of x gets close to L. Arbitrarily close, he adds. Does it have to equal L? Okay, Dina says it doesn't have to equal L. Lace said it has to get arbitrarily close to L. Okay, so now let me try this. Is this right? As x approaches a from the right, f of x must get arbitrarily close to L. Is that the correct definition of limit? Okay, why don't you like arbitrarily? So arbitrary? Would you prefer infinitely close? Okay. Infinitely close. We know just as much what that means. Okay? Okay, so it has to get infinitely close to L. Is that right? Was that how I said things? Was it that you have to get infinitely close and stay infinitely close, right? That was the other half of it. Okay? So part of the limit definition was you have to get infinitely close, but you have to stay infinitely close. You're not allowed to get really, really close and then jump away. Right? Get really, really close and then jump away. Yeah. You guys don't know who Bill Cosby is, maybe. He used to have this great bit about men and women, and he would say he was talking about Adam and Eve, and the woman is always saying, "Oh, you come here, come here. Oh, get away, get away, get away. Oh, you come here, come here, come here. Oh, get away, get away, get away." Okay, this was his. It was very funny. I don't know. When I was a kid, I loved it. Okay, in any case, right? The limit, when you have a limit, right, you're not allowed to do that. Right? You can say, "Come here, come here, come here," but you can't say, "Get away, get away, get away." At least not for long. Right? In the long run, right, as you get really, really close to A, okay, from the right side, You have to get as close as you possibly could want to get to L, and you have to stay that close. Okay? You can't jump away again. Okay? It's no good to be going boom, boom. Okay? You have to stay in there. Okay? So that's what this limit meant, right? And of course, okay, the left side was the same. Okay? And so the two-sided is just saying, okay, as close as I want to get to L, all right, I can get close enough to A so that my f of x gets that close to L and stays that close to L. Right? Okay, I can get infinitely close to L and stay infinitely close to L by letting my x get infinitely close to A. Okay? Now, on Fridays, we do a very precise job of defining these things, actually. Right? We say, okay, for any epsilon greater than 0, we can choose a delta such that if x is within delta of A, then f of x is within epsilon of L. Right? That's the formal definition that we're not supposed to write down in this class. Okay? But if you want to know it, ask the people from the Friday session, and they'll gladly write it down for you. Okay? We're going to use this as our motivation, okay, for defining convergence of a sequence. We're going to write down the limit as n goes to infinity of an, right? So this is the nth term in the sequence. Okay, so the limit here equals, well, it's a good a with no index. Okay. Okay, what are we going to mean by this? Okay, we're going to write this if, well, informally, we're going to say as close as you want to get to A. Okay. We can go out far enough in the sequence so that you are that close to A, and you stay that close. Okay. You get arbitrarily close to A, and you stay arbitrarily close to A. Okay. So if one can get and stay arbitrarily or infinitely close in Dina's case. Get and stay arbitrarily close to A. Okay, now this is the informal way to write it. Okay, I'll write down a formal way to write it. So let's write down a more precise version. Okay, sometimes this is helpful, sometimes the more precise version is helpful. Okay, so i.e. Okay, now I'm going to use a Greek letter here for those of you not in my Friday class. You may not have seen this too often. It's the Greek letter epsilon. We usually use it to denote a small real number. Okay, so remember the upside down A meant for all. Okay, so it says for all real numbers epsilon greater than 0. Okay, remember this backwards E meant there exists. Okay, so there exists some n, which is going to be a natural number, such that okay, now I write down here an minus a, and I put absolute values around it. And I say less than epsilon. And I'm going to write for all n greater than or equal to big N. Okay, now I have to explain this. Okay. You should always say explain yourself. Okay, so my definition was supposed to be that I can get and stay arbitrarily close. So this epsilon greater than 0 is my way of translating the arbitrarily close. If you say get this close, then you're saying get within some number. Okay? That's my epsilon. Okay? Now, go down here. When I say less than epsilon, right? These things, whatever this is, less than epsilon, right? This here is the distance between an and the number a. Okay? If you ever want to know the distance between two numbers on the real number line, you just subtract them and take their absolute value. Right? Why the absolute value? What's that? Displacement. What do you mean? Yeah, we don't want distance to be negative, right? If I say, what's the difference between 1 and 3? What's the distance? 2. How did you do that? 3 minus 1. What if you did 1 minus 3? You have to do absolute value, right? You have minus 2. The absolute value takes care of that problem, right? If you have the absolute value, it doesn't matter what order you do the subtraction in, right? Somebody else, somebody who's smart says, oh, of course, just take the bigger one minus the smaller one. But this, you don't have any of that problem, right? The absolute value just says it doesn't matter what order you do it in, right? You're in some backwards country where you do everything the wrong way. Put absolute values, it's all good. Okay? So this says that as close as you want to get, I can get that close by going out far enough. Okay, that's this little n here, though, is supposed to be bigger than or equal to this big N. Okay? So I have to go out far enough, but I can get close. But then this bit right here, this upside down A, right, which means for all, that tells you it stays close. Okay, because this isn't just it's not just you find this N, and if you go past it, you can get that close. For all N past this N, you're going to be that close. Okay, so this says you can get close for some N, and you stay close for all the N past that big N. Okay, so this is the precise mathematical way to write down these things. Okay, but I just want you to, intuitively, it's just the sequence will get close and stay close to that number. Okay, does that make sense? Gets close, stays close. Okay. So in the nice case where this limit actually exists, we say that the sequence converges. So if the limit as n goes to infinity of an equals a for some real number a, then we say that the sequence an converges to A. And if we don't know what A is, we can just say it converges. Right? I might tell you I have a sequence and it converges, but I don't tell you what it converges to. Right? In fact, I might ask you, what does it converge to? Okay, so let me give you a sequence. 1, 1/2, 1/4, 1/8, 1/16. You can see where this is going, right? The nth term is going to be 1 over... Actually, let me leave the 1 off so that this formula I'm writing is correct. 1 over 2 to the n for the nth term. And it keeps going. Okay, what is the limit? So let's see, we'll give a name. We'll just call it an. Okay, that's our sequence. Okay, what's the limit as n goes to infinity of an? What do you think? So you think this sequence gets and stays arbitrarily close to 1? What's happening to these numbers? Yeah, 1/2, 1/4, and 1/8, right? Oh, I'm not summing yet, right? There are no pluses around. Yeah? Okay, we're not series, but you're right, of course. If you add the series for this will be 1, but you're anticipating me. Okay. Right. So you're saying these things are getting close to 0, right? Are they getting arbitrarily close to 0? What, do they stay arbitrarily close to 0? Sure, right? If you want to get within 1/1,000,000th, right? There's a very easy way to do that. Just go out to the millionth place, right? Then you'll have 1 over 2 to the millionth. You're certainly within 1/1,000,000th, right? And you never get any further away, right? This always gets closer to 0. So this thing converges to 0. So an converges to 0. What about our sequence of natural numbers? Does that converge to something? Right? Well, remember, we've only talked about converging to a real number. Right? It has to get and stay close to a real number. Does it get and stay close to a real number? No. Okay, so it doesn't converge. Okay, so what should we call it if it doesn't converge? Yeah, we say it diverges, right? It's a divergent sequence. Okay, so a sequence AN diverges if it does not converge. Isn't that a great definition of something? Okay. Just like the finite and infinite bit. Yeah. When is it infinite? When it's not finite. When does it diverge? When it doesn't converge. Awesome. Okay, now, within the world of sequences, there's a lot of them. It's going to be very easy to find ones that diverge, but that diverge in very different ways. So, for instance, right, we just saw that 1, 2, 3, 4, this diverges. On the other hand, let me ask you, what about this one? 1, minus 1, 1, minus 1, 1, minus 1, and so forth. Right? It goes between 1 and minus 1, just alternates. Does that converge or diverge? Why does it diverge? That's because it's not converging. Ah, that's a great answer. Okay. How do we know it's not converging? Yeah, well, if it's converging, right, there has to be a limit. There has to be some number that it's getting close to. Well, it gets close to 1. 1, 1, 1, 1. What am I missing? It's getting close to 1, that's true. Doesn't stay close, exactly, right? It's got to get close, it's got to stay close. It doesn't stay close. Hops back and forth, 1 to minus 1. Okay? So this diverges. But these diverge in very different ways, right? This one is diverging in a, I don't know, in a way that you could actually describe to somebody very easily, right? Namely, it goes to, what does the sequence do? I mean, you could tell us to just about anybody and they know what you mean. That sequence, what's the limit of that sequence? 1, 2, 3, 4, 5. It goes to infinity, right? Everybody's going to say the same thing and everybody's going to know what you mean. It just keeps getting bigger and bigger, right? And if I wrote minus 1, minus 2, minus 3, minus 4, minus 5, blah, 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 what would be the limit of that sequence? Minus infinity, right? It diverges, but it goes to minus infinity, right? And everybody would know what you mean, okay? But this one, this is a little harder to explain to somebody what's going on, isn't it? I mean, it's not that you can't, but it's just a little bit harder. Okay, so let's at least write down what we know, right? Namely, that there are some of these limits that are infinity, okay? And we want to again try to write down what it means to diverge to infinity. Okay, and I'll just write it for infinity, but you can mimic this for minus infinity. Okay, so let AN be a sequence. So the limit, what is it going to mean? The limit, n goes to infinity of AN equals infinity. Well, let's try to mimic what we did. So first, let's do the informal. To have a limit of A, it's supposed to get and stay arbitrarily close to A. Now, infinity is not a number, so you can't get arbitrarily close to it. All right. So we have to change that a little bit. What characterizes infinity? How do you think of infinity? A lot, right? It's very large. Right? So instead of saying that we want to get close to infinity, right? Maybe it's better to say we can get arbitrarily large, right? We can get as much as we want. Okay, that's what infinite intuitively should mean, right? So we'll say this. Okay, so the limit is n goes to infinity of an equals infinity if the terms get, leave a little space, arbitrarily large. Okay. Why do I have to leave space here? What am I missing? A word! I love it. Yes, 2 words. One of them's just a conjunction. Well, look at the original one that we did. And stay, right? You can't just get arbitrarily large, right? Let's say it went up, 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 boom, right? And then up, 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 up. I'm not talking about the stock market here, okay? Okay. We don't allow that, right? There are no plunges anymore. Okay. We have to get and stay arbitrarily large. Okay, but of course, there always has to be the IE here, because we don't know what this means. So we're going to try to write down precisely what it means. It's not going to be that hard. I think this one's much harder. Okay, now, Dina argued that we couldn't add up all the natural numbers and get a natural number. And her argument was, if you could, then there would be some natural number, k. Right? That's what it would add up to. And then she said, yeah, but add 1 to it. Now you have something which is bigger than k, so you get a contradiction. Okay? So we use the same thing here. To be arbitrarily large means you give me a number, and I'm going to get past it. All right? You give me a k, and I can show you that sequence gets bigger than k. Okay? So i.e., for any, say, it doesn't really matter if we use real numbers or natural numbers. So let me just say natural numbers. For any natural number k, there exists a natural number n such that an is greater than k for all n greater than or equal to n. Okay, so what is, see if this is actually giving us what we want. Okay. So the limit of the sequence is infinite if the terms get and stay arbitrarily large. That's what we wanted to mean. And this says, for any number that you put down, eventually I'm going to be bigger than that number. So I'm going to get arbitrarily large, right? Because you can pick any natural number here. You can make it as big as you want, and I'm going to get bigger than it. Okay, so it's getting arbitrarily large. How do I know it's staying arbitrarily large? Right? What's the key? What's the key ingredient here that tells me it's staying arbitrarily large? Yeah, right? This upside down A, which means for all. Okay? So this says that an is going to be greater than k when you get up to this big N. But this for all says that it's going to stay bigger than k once you get past that big N. Okay? It's going to get large and it's going to stay large. It can never return again. Okay? That's the key. Okay? So this N, right, that's the get part. This for all is the stay part. Okay? It gets large and it stays large. Okay, so we have to stop there. Okay, So tomorrow we continue. We're going to give some more definitions for sequences, building up towards deciding what kind of series we can actually talk about, that is infinite series.